Thank you, Michelle, and welcome everybody to this very exciting short course and the exciting workshop we're going to have afterwards. I want to acknowledge the contribution of my other two co-leads, the other two co-leads of the workshop, Professor Sergio Pellegrino. Sergio, where are you? Give him a round of applause, please. And Dr. Jim Like from the Air Force, also the other colleague. And since it's already time to begin, I will introduce the first speaker. First speaker is Dr. Adrian Stoica, and Adrian is a JPL senior research scientist and also a NIAC fellow. He has been a JPL for 18 years and has led a number of technology development projects for NASA and Department of Defense, including 5 of them as PI for DARPA. His areas of interest are human-centered systems, advanced computing, and robotic systems. And he has the first talk. Adrian?
Transformers. It's an energy projection system with some specific characteristics. It changes shapes, like in the movies. It changes shape to adapt to the needs, and also to basically the need is to transform the environment. So 2 meanings: transform the environment and transform itself. Exploration of space means not only traveling very far, but also facing some conditions that are very extreme to us, both to us as humans, but to us also as technology developers, because the robotic systems that we send there very much have followed the technologies that were developed here on Earth for Earth use. I don't remember exactly whom to give credit for this chart. I've stolen it many years ago. But it reflects at least 2 of the conditions that make the exploration hard: the temperature and the radiation. And the temperature, there is a lot of meaning there also. It could be hot or cold. It could be hot and cold changes in the same, say, in the same day. It could be the same place. But just the same place, meaning the same planet, for example. It could be very hot on the surface, for example, like on Mercury, but if you go inside the crater at the pole, it could be very cold. So surviving the extreme environments or extreme space environments is one of NASA's space technology grand challenges. I'm going to focus on the craters, and in the craters and the caves, because that's where there is a chance that the things are well preserved. I was taking some cough medication this morning, and I see they're written as a store in a cold, dark place. So I guess that's where we also store things, but if there is a big chance that we also find there ice, which is important for exploration, for any kind of a mission. That's why we are thinking of having a lunar outpost near to the south pole of the moon, where we suspect there is ice in the craters. Also, going away from the surface, there is less of the effect of the sun and the degradation that happens at the surface there. So very interesting things. But on the other hand, the absence of the sun in that locations makes it difficult to power the system. So if in the absence of a solar, we may need to go to a nuclear type of a source. But imagine that, for example, you can project a favorable microenvironment around the robots that explore these permanently shaded craters or the depth of the caves on Mars or Moon or Mercury, and allow them to survive the extreme cold and the darkness out there. Suddenly, unexplored areas of the solar systems, which are kind of within reach at a close distance, but also hard to operate in right now, become possible. So we can find water traces of life and various clues of the past. This may be coming possible with these transformers. This is a new class of robotic systems that can change shape and function to project resources needed, energy needed, to induce a favorable microenvironment around the explorer at the locale where we need it. So it's like just in time, just at the location where there is an interest. So I mentioned the solar and the nuclear. So basically, the simple algorithm is here. Do we have energy? Well, let's say solar energy. And if yes, well, we use solar panels. And no, well, we have to bring some other source of energy. And in this particular case, for example, a radioisotope thermoelectric generator, or an RTG, or sometimes we call it multi-mission RTG. So MMRTG is the acronym for it. So if the solar energy is available there, we use it and we capture it. And if not, then we have to bring something. But the transformers adds a new perspective, or the energy projection systems add a new perspective. So basically, it's still there's no sun over there, but basically the idea is to use a remote resource that projects is projected into the place of interest to induce a microenvironment, and I'm avoiding the word microclimate because it has a slightly different meaning. So it's not sunny, but we bring the sun in there. So as opposed to using a local resource, as in the first case, we use a remote resource that's been bringing. Instead of coping with the environment, we change the environment locally. So that's kind of what energy projection system could do. And discovered not long ago, this mission, Lunar Flashlight, selected by the NASA Advanced Exploration Systems, which it actually has this target of mapping the lunar south pole for volatiles, and is the first mission to use a solar sail. It's an 80-meter square solar sail used as a reflector for science observation. So basically, it is reflecting the sun into this polar area south of the pole of the moon, and basically it is for science purposes to measure the surface reflection and composition, in particular to locate good targets for future missions, in situ missions like landers or rover-borne measurements, where there is sufficient quantity and near enough to the surface to be operationally useful. So this is very interesting because right now it's done from the orbit, but then we are trying to find the best places, and potentially we could do the same projection in situ. Even though we thought it is a neat idea, and it's not necessarily a new idea, but I'm going to focus a little bit with its meaning to the craters. About 100 years ago, the Norwegians who moved in a narrow, deep valley in a place called Rjukan, they thought, the founder of that village thought that it would be good if they put some form of reflector to get the sun into that valley that is shaded for many, many months in the long winter in Norway. So it has a lot of effect even on the mood of the people over there. So right now, actually, they implemented that. I think the Italians actually were the first in this other city, Viganella, both in deep valleys. So basically, they built this reflectors that are projecting, yes, somewhere, that are reflecting in the Rjukan case. They're projecting, thank you, a 600 square meter beam into the town below. So these are the mirrors. Obviously, they're heliostats, so they are tracking the sun and projecting somewhere where the locals gather and are having a good time. And now they can see the sun in winter. So this is something that gets people excited, and it gets the students excited. So we have students who try to say, okay, let's do a model, or let's see how this kind of works. So, well, the sun was not coming just above the horizon, but in order to do that, they put some mirrors to bring it at the ground level. So from this moment on, the sun comes like in here. And now these are the transformers, or these are the reflector mirrors, and this is the crater. So basically, these are
slowly moving. And here is the rover. And you receive the sun, and it's moving. So that's an illustration of the concept that the students found quite funny. And they had a lot of good time with it. Same story to the cave. So basically, or to the lava tubes. So you have a reflector somewhere at the mouth of the cave, the entrance of the cave, and then you're projecting down, and then you're projecting further, and potentially you may actually cross corners, so, or go around the corners. And again, this is apparently not new. I heard that when you go to Egypt, they're telling you that this is how they worked in the pyramids. They got in because there's no trace that they used any kind of candlelight or anything. And that, I don't know if it's true or not, but what we know is basically more than 100 years ago, here in California, in the Sulphur Mountain, the engineers used mirrors to reflect the sunlight into this tunnel, which is like 2,000 feet long tunnel. And this was used for lighting and alignment. I mentioned kind of going around corners. So I told my students, say, you know, my office is kind of too dark. I don't get, so I'd like to bring me the sun inside. So they say, okay, well, let's see the experiment. So there was a beautiful sun there, and they started putting mirrors. And by the way, these mirrors are from a heliostat that you can buy for $300 right now. So you can see they find all these kind of solutions, and this guy is kind of board, and it's putting in here, oh, this is not in my office, this is just another rover. They like the rover. So I just think, you see, in a dark place, around corners, you can get to that. So now, so what kind of questions are important, or for example, for mission scenarios of exploration of the permanently shaded polar craters or moons? What are the requirements for energy projection systems or transformers in this case? What measurable benefits they can bring to the mission? And of course, a very important question which we would like to address into this workshop is how to build them. In terms of impact of this, we could look at it from a variety of perspectives. We could look at it from the point of view of frontiers of exploration, and as I mentioned, it opens new frontiers of exploration and scientific discovery in a relatively close proximity, moon, but hard to reach destinations. We can move around the crater, but it's inside where it's very exciting to be, and we want to go in there. From a robotic control perspective, you could look at it as advancing the state of the art in controlled projection of sunlight on a moving target, because as opposed to the villages in Norway, this time you have to do a heliostat, but also to track a rover. It advances reconfigurable robotics, the fact it's doing progress into the shape-changing techniques, which relate to some extent to soft robotics or origami robotics. It's important for materials and embedded electronics point of view, because we are thinking here of a change from what it was before e-fabrics or e-textiles, electronic textiles, to robotic textiles or transformer textiles or transformer fabrics, which is basically a combination of not only electronics, but also the sensors, the actuation, the power, so everything in the layer, which makes this fabric more sophisticated than the electronic portion of it. From a system perspective, again, a multifunctional system with sensing, actuation, and so on. And obviously from a solar concentration, a variety of DOE applications. In terms of potential mission, so this is the south pole of the moon, and this is the Shackleton Crater, which has been proposed as a base for landing for NASA. And there are a couple of points of quite a big interest around this area on the rim, because they have sun most of the time. And we're going to see later, at most, you'll have 2.5 days in one of these points. I think it's called A2 in the dark. So it's a good thing to charge and to reflect to the sun into it. There are two other things important to note, two other features in here, which is this point in here and this point, the Leibniz Plateau and the Malabar Peak, which basically they are in permanent view of Earth. In other words, the Earth is seen from there
in one of the cases, 100% of the time, 100% of Earth is seen in there, which makes it good as a communication point to Earth, of course, continuous communication. Not only that, another interesting thing is from here to here, you have a direct line of sight. So theoretically, you could go in here, reflect the sun, then talk to here, talk to Earth. So these are some numbers that show the characteristics of these features. These are peaks like 4 kilometers and 6 kilometers tall. And for Shackleton Crater, other piece of information that you can see here is about 20 kilometers diameter. So to get to the center, let's say, you have 10 kilometers drive. And again, the crater floor is never illuminated, but you have almost permanent illumination on the rim. This is a bit more detail of the Shackleton. So the South Pole is basically in the Shackleton Crater, and excuse me. And you can see here an elevation map. So it's basically, I guess, close to about 4 kilometers deep, and as I mentioned, about 20 kilometers in the diameter. Here you can see a little bit better. So the elevation is maybe about, it's going up to maybe about 500 to 1,000 meters. So it goes up and then goes down in the crater. So this on the rim, it's a very good illumination, and you can see here in yellow, it's basically, or the lighter the color, the more permanent illumination you have on the rim. So, and this is again a different view of the region, and in particular, these two areas of or this A and B are areas of interest, in particular points A1, A2, and B1, which have the highest multi-year average illumination for the South Pole sites. But in particular, A1 sees 100% of the solar disk 86% of the time, and the maximum period of continuous darkness is 2.5 days. And the longest periods of partial darkness, which is basically less than 100% illumination, is 5 days in there, 5.5 days. So the concept, I guess, is the following. You have the sun coming, you have a heliostat of some sort, and then you have a projection system that helps the rover go in, perhaps even illuminates the path, and it's also powering the solar panels, and perhaps even heats the rover itself. And yes, there is a small problem in there. The problem could be, what if you spill some of the energy around in the crater and you're melting this ice that you came here for searching? And I found actually an interesting article in there which tells you about the temperatures for sublimation in this area, and how much time you can keep, or to what temperature can you raise it. So again, we are talking about 40 Kelvin, 40, 50 Kelvin. And even if you increase to 170 Kelvin, for example, and I think I have some charts in there, it takes some time until, I think it's in the order of 30 minutes or so to sublimate a particular amount of water. So in other words, if you are very careful and you do it for a short time, you may be able to avoid an increase in temperature that it's wasting the resource you came there to explore in the first place. So I guess the exploration, I think I have a movie in here. So let's try to play this. Everything that it was in the previous chart can be shown during the movie. Well, if I can play the movie. So we are landing somewhere around the pole, and basically a rover carries the transformer to the rim. And at that point, the transformer starts deploying. And again, here it's one arbitrary shape, and I think that is going to be a little bit bigger than what it is in this cartoon. And then it starts kind of powering and charging or recharging a little bit more from the solar panel of the rover. And then the rover slowly starts descending in the crater, perhaps even on the path illuminated by the transformer. So in other words, it's indicated by the transformer, who may still have a better view than the local view of the rover. And then again, the transformer is a heliostat, so the sun is kind of moving in this direction in the cartoon, and also it's kind of tracking the rover. So at all points, you need to know where the sun is, you need to know where the rover is, and find the best position such that the light reflects into the rover. So in terms of emission studies, you can think of, well, we could have one lander, or we could have two landers. If we have one lander, we could, the transformer could be on a static land, and the rover could drive off. Or you could have a mobile transformer itself and the mobile rover. Or you could have a sky crane landing to put the rover in the crater, and then you can fly to the rim, and the transformer, or the other way around. P here denotes the precision landing. And then in these cases, when you have a mobile, you have a self-actuated transformer, rover, and so on. If you have two landers, you have one for a transformer and one for the rover. You can have simultaneous landing and so on. So all these cases are presented in here in some detail, but more or less they are summarized into this bigger table, which I probably have to read to you because I'm not sure. Well, I read the most important part. I don't think you can see it in the back. But here is for one, this region is for one, and this is for two landings. And in particular, in green, you can see the optimal case, which is, I think, selected by the lowest risk. Risk is this category here. So again, after a variety of categories, it's the landing site, the precision, high precision or low precision, the mobility is static or mobile, timing, it's simultaneous landing or in a sequence about the trajectory, if it's direct or low energy, of the difficulty of operation, and so on. So this particular one is actually the overall best, and this is the scenario that we're going to discuss later, which is basically the lander delivers a mobile transformer and rover near the crater rim. It's kind of low precision landing, and then it's a mobile transformer, and it's one critical event. Then the transformer is position deployed and checked out before the rover drives off. So, and still remains the risk of the rover driving in, as opposed to the rover being deployed directly in the crater. So we could think of the size of the rover, and I guess three sizes have, these are the sizes for rovers on Mars, obviously, but basically you have a small category of a rover, a Sojourner type. You can have an MER type of rover, Mars Exploration Rover, or you can have an MSL type of rover, which, again, this particular MSL is actually, in the current mission, is a nuclear power. But you see that the level of power needed in this case is, it's about 300 watts power needed for MSL, and about 100 watts power for MER, and I guess about 25 watts of power for Sojourner. So the nuclear, the RTG comes with some penalty. The penalty is also a mass of, in this particular case, 40 plus kilograms, and also a small penalty of cost of maybe 45 or so million. So, which means that you need to have a particular type of emission in order to afford an RTG. So very small rovers perhaps cannot carry, and I think there is a table here somewhere which shows you that if the rover is very small, well, you can't have clearly an RTG. But not only that, even a battery you may not be able to carry, because the size of the battery, in order to keep the rover warm, let's say for 2.5 days or nights, it is of a certain size. So what parameters would we be interested to look into if we look at the transformer? So solar panel size, how big is the solar panel on the rover? What's the size of the transformer itself? What distance can you operate to? What can you say about the reflectivity of the transformer? What kind of sensors do we need? What kind of actuation? What kind of a pointing control performance for the transformer? These are some of the things of interest. And if we think of from a point of view of an optical analysis, if we look at the illumination conditions with such a reflector, which gets the sun into the rover, and we're looking at what is the angle subtended by the sun, which in this particular case is 9.3 milliradians. The sun, as you go with the rover further, may see a smaller portion of that, or different said that the sun illuminates a bigger region around the rover, not only the rover itself, which gives the calculation of these curves, which allow us also to say something about the size of the needed reflector or transformer. So this, for example, is for different diameters of the mirror in here, or mirror or reflector or transformer or energy projection system. And here you have the solar radiation. Irradiation here, it's about 1,300. It's approximately the same as we have for Earth. This is per watts per square meter. And the different curves are presenting different distances of the reflector to the rover. So this is for the very small, actually, dotted line here is for 300 meters, for 1 kilometer, for 3 kilometers, and for 10 kilometers. What does this curve say is that if you want to obtain, let's say, 1,000 watt per square meter, you need to be around here, which is maybe about 70-meter diameter of a mirror. And it requires about 100-meter diameter if you want to obtain the same solar radiation as on Earth. So it's a big mirror if you want that. However, there is good news in the sense that, well, I don't necessarily have only a solar reflector of 1 meter, but I can have, a solar panel of 1 meter, but maybe I can have it 2 meters, or in this particular case, 6 meters. So in a calculation of a 6 meters with 16% efficiency, which is a relatively conservative thing, then basically we could look here. So this numbers become the same in here, because 6 times point multiplied with 0.16, it's about 1. We could look directly at the curve to see what is the size of the reflector to obtain a particular power. And if we think of an MSL size of 300 watts, we get to this point, which is about 40-meter diameter. So 20-meter radius, about 1,200 square meters. That's the size needed on a reflector on the rim of Shackleton to beam in 10 kilometers in the crater. If you have a smaller one, 20-meter diameter, you get 100 watts. And again, this is for 10 kilometers. But if you look at these curves, you could stay, excuse me, if you are, for example, at in a curve of a 30-meter diameter, you get the full solar intensity, for example, up to 3 kilometers. So you can see. Oh, is it the 3 minutes for me? I just see the orange right now. All right, so, the good news is that you could get to 10 kilometers with a 40-meter diameter. And from the point of view of the thermal, I mentioned the 2.5 days of darkness, or the night that you need to survive the minus 200 degrees Celsius. Basically, looking in here, the type of battery that you would need, this is the calculation based on the surface of the rover and how much heat is losing. But you're looking at, for example, a 1,000-kilogram rover, and you need about 80 kilos of battery to, losing at about 15 watt, I guess, per. But another context is for about 10 kilograms, you need actually 11 kilograms of battery on a 10 kilograms rover, so obviously that is not a good solution. So again, something needs to be done, but you can't do it so small. So what do we make these transformers of? So I mentioned this transformer fabrics, and the fact that on a film that is thin, we demonstrated all the subsystems. We demonstrated, I mean, when I say we on Earth, not JPL, but basically the electronics for computing, the power, the solar, the antennas, and so on. Interestingly, 40-meter diameter is also what the European Southern Observatory wants for the size of a mirror there, and for the main mirror. And it's made, obviously, of smaller pieces, of segments. It's about this size, 1 meter across, but 2 millimeters thick. 2 millimeters thick is an important number. I'm going to change a little bit. So I'm trying to find here. Well, it looks like I may have. Here was the thing. So this is the size that I measured for 40-meter diameter. So if I can have something which is 100 microns, it will be a very small volume, you know, a tenth of a cubic meter. Okay, so let's say that we are not so stressed, and we get it a little bit larger. So 1 millimeter, you still get 1 cubic meter. That's kind of a volume I like to get with a rover, or smaller than that, in order to be feasible. We don't want it to be 10 times bigger than the rover. So as you can see, this type of dimensions are achievable. So in that case, the context we are talking about is something like this. I want it to be packed in here. This is 1 meter, and this is the 1,000 square meters. So that's kind of a view of and how do we do this in terms of origami, how we fold it. That's kind of a subject for discussion in here. The science that we can obtain from this, well, it shows you for the large craters, and you can see it for mid-sized craters, but also for the caves and for the small caves. So basically, this is the last slide. It's saying the problems that we need to deal with relate to the heliostat tracking, to how do we change the shape, what kind of measurements we need to have at the transformer to find the position of the rover, position of the sun, and how do we communicate, what are the folding or unfolding options, what's the actuation, how do we deal with different environmental conditions like winds on Mars, dust that puts on these reflectors, or how do I go around the corners in the multi-hop things. And all these scenarios are something that we'd like to explore. How do we go into inside the lava tubes, Mars, Mercury we didn't address, if we have scenarios with multiple transformers, and how do we actually best compare with the RTG solution. So thank you very much.